I'm a research scientist at Valeo.ai, and today I'll be covering the different works that basically work on like image encoders pre-training from videos. Um, so this talk would basically be an overall review of the different works that have been using self-supervised learning methods or have been pre-training in a self-supervised setting using videos. It's basically divided into three parts. The first part is called integrating vision and motion. Then we have visual prediction, and then finally we have videos for unsupervised, image features. But before diving into each of these topics in detail, I just want to talk about a very nice, interesting experiment in neuroscience from researchers Held and Hein, and this was a very interesting experiment that I was also inspired by one of Professor Christian Grauman's talk. In which they were trying to study how kind of ego motion helps in developing really strong visual perception. So here you could see that there are two kittens. One is an active kitten and one is a passive kitten. And so the kittens were basically tried to be kept in the dark from birth, except for a couple of hours in a day, where they would actually sit on this carousel, right? So you can see on the left there's an active kitten where its legs are kind of free, and then there's a passive kitten who's kept on this basket with which is completely covered and it doesn't have its motion. So the only way it kind of moves around is by kind of following this active kitten. And they were trying to study basically how does this help in visual development, in helping depth estimation, and also response to external stimuli and so on. So naturally, what they found was that the passive kitten doesn't do well in any of these evaluations on depth estimation or say response to external stimuli, while the active kitten just outperforms it completely. So what is the message here? So they basically say that the key to visual perception. So both of these kittens basically see the same thing. Their visual experience is similar, but the active kitten has its own ego motions, and its decision about that ego motion. So the message here is that for proper perceptual development, it requires leveraging these self-generated movements in connection with the visual feedback. And this means that for visual development, it's not enough to look at things visually, but also experience the physical context of looking at these things. So the key take home message of this kind of experiment was that for the proper visual perception, ego motion coupled with active interaction really helps getting really strong feedback or learning, having good visual perception. So based on all of this kind of there were a lot of researchers that were inspired and had several line of works along this observation. So and they kind of translated into how you could basically teach deep learning models uh, based on ego motion versus the active interaction. So they were trying to find a connection between how we kind of move around and how the visual surroundings change in this perspective. So there are several ways to kind of collect the ego motion. So one is the autonomous vehicle with multiple different cameras around it, and this kind of also helps captures a lot of, let's say, videos in the wild. We have your own mobile camera nowadays that captures really good quality high resolution videos. And finally, we also have another setup of these head mounted cameras. uh, there have been very popular data sets such as Epic Kitchen and so on, Assembly 101 and so on, so where they were trying to collect all these video data sets using this head mount camera. So this brings to the first very interesting line of work by Pulkit Agarwal and colleagues. It's called Learning to See by Moving in ICCV 2015. And imagine that we are standing in front of the very famous Duomo in this beautiful city of Milan. And now we kind of eventually, after looking at it and admiring its beauty for a few minutes, we kind of now move around and away from it. And then this kind of changes the perspective, or gives us a different perspective about how the Duomo now looks, from a different standpoint. So the idea here is that when we were standing in front of it, we had a we had a different perspective of the cathedral, versus when we kind of just move around. And this kind of although the object here of interest, or the cathedral, still remains the same, but we view it from different angles, and this creates a very unique perception around it. So what the authors of this work did was kind of given two different frames, or from the same video clip that offers two different perspectives of the same object. They kind of predict the camera transformations that change from the frame 1 to frame 2, right? So they have a Siamese network. uh, they obtain the features at the output layer, have a projection head, which in the recent SSL terminology it's called projection head, that we then use to kind of predict the transformations that has taken place from frame 1 to frame 2. And during inference, what we just do is discard the projector at the head, the projector at the end, and then just use it for downstream tasks. And this is how the model has been trained end to end in a self-supervised setting. Well, building upon this idea, the so sorry the objective of the work was to kind of, given pairs of images related to the same ego motion, it should also be related by the same feature transformation, right? So in other words, it kind of also enforces some sort of ego motion equivariance. And this is something also kind of very interesting that led to the next work, which is learning image representations tied to ego motion in ICCV 2015, where again, let's say that we are moving across from, let's say, from two different locations. We are moving from location 1 to location 2 in front of the Duomo. We observe that there are like multiple different objects that have remained the same, with, but have different, like, viewpoints and so on. So we want to enforce equivariance of these objects even in the feature space. So here, for example, the Duomo remains the same. The statue over here, when we look at it from the back versus from the side, remains the same, because it's the same object from two different perspectives, and along with the buildings on the right and so on. So the idea here would be that when learning these kind of equivariants, when we kind of enforce this equivariance, it kind of enables the model to learn different aspects, such as depth and 3D geometry. At the same time, it also helps it to learn semantics and the context. And all of these three things coupled would kind of be really helpful and acts as a key for recognition. So how do they kind of train these models? So again, we have the two frames from the two different timestamps. We pass it through. We have a Siamese network, and what we basically do is we kind of learn the transformation from image one, or pass it through a linear layer, and then just apply something as simple as a cosine similarity between them, and try to train this end to end. And this kind of also helps. And in the same way, during inference, you kind of drop you just pass a single frame to the deep learning layer model, and then just apply linear probing and so on for different downstream tasks. uh, so it would be interesting to kind of, so now, with all of these different ego motion equivariants, learning camera transformations and so on, it would be interesting to kind of investigate if it's actually possible to learn better visual representations if now the instead of, let's say, along with this, if the agent kind of can actively decide how to explore the environment on its own. And this brings the concept of active recognition. And so for I just want to explain the terminology of active recognition. Is the term actually means that to kind of intelligently make these motions or decisions about how to move, that will help these recognition models succeed faster. Um, and the problem is that most of these kind of image recognition models still consider have these nuisance factors such as pose, lighting, and viewpoint changes. And this can become avoidable factors in the active vision settings, right? Since in principle they can just be overcome by kind of moving in the right direction, right? So here is another interesting line of work where it's called look ahead before you leap into an active recognition by forecasting the effect of motion. So so given these two images, you and we want to kind of understand or predict what these kind of objects are. So it could be either a cup, a bowl, or a pan, because from the top view they kind of look the same. So 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 this is where activision active recognition comes into picture, right? So if you want to kind of recognize or pass like train image recognition models, it becomes difficult when you are from this perspective. But now once you kind of when the agent automatically kind of moves to a different location, it sees these two objects from two different from different viewpoints. And now this makes it so much easier for the model to kind of recognize these objects. And this is a kind of a very interesting way um, to kind of do recognition. So the idea would be to kind of we the idea is to basically learn a policy which would basically tell an agent in which direction to move to kind of recognize things more rapidly. And this is an example of an end-to-end active recognition. So here you have the image, and you basically train the agent to kind of make this decision as to kind of from which is the new viewpoint, um, to kind of view this object to make decisions faster and more accurate. So ego motion equivariance is kind of used to enforce to select the next best view. So, a brief recap from all of these different works is that visual learning basically benefits from the context of action and motion in the wild. It's a form of a continuous self-acquired feedback that helps it to kind of develop these very interesting perceptions such as 3D information, semantics, and context. And they also show that in these line of works that by enforcing this ego motion equivariance, it boosts performance across multiple challenging recognition tasks. The next set of works, we can kind of term it under the visual prediction. And the first work is anticipating the future. So we have this diving sequence from a very famous Olympian. So given the context, that the Olympian performs these different flips. The next step is to kind of anticipate what would be the next step, right? So it could basically be that the Olympian performs another set of flips, or they would directly like dive into the water, right? So kind of ensuring or predicting that which would be the next frame would act as a very useful signal to kind of pre-train your model. This would basically also enforce temporal cues in the model. So this is a very interesting line of work from Carl Wondrek and colleagues, anticipating visual representations from unlabeled video. So what they basically do is, given a video clip, they pass in the current frame through a convolution layer, and they have the future frame. They again, obtain visual representations of the future frame, and then they kind of use, so using the current frame, they try to predict the features corresponding to the next frame, and they apply a simple loss, and they train their model end to end. And I would also like to mention that this was one of the first works that introduced a very large scale data set, a new video data set of 600 YouTube hour videos, and this kind of, really enhanced, the learning on video self-supervised learning. The next set of work is, following a follow-up, or let's say, also inspired by this way of anticipating the future, is learning to track. So the idea would be that, if we are, the object, as it kind of moves along time, if we are able to like track it efficiently, we could use the features of the objects from two different timestamps, and apply a simple contrastive learning loss to train the model. So the idea would be that we have a video clip, let's say, and we use a simple, off the shelf object tracker, and the idea would be that uh, an object from the object from the first frame would basically act as an anchor, and the object from the last frame, the same object from the last frame, would basically act as a positive of that particular anchor, and any random crop from anywhere in the video or in the batch would basically act as a negative. And this would, simply, all these, the triplets of positive, negatives, and anchor could be used to perform simple, we could use a simple triplet loss or a contrastive loss to train the model, end to end. And this is the work of Wang and Gupta. It's called unsupervised learning of visual representations using videos in ICCV 2015. And a brief recap of all these works is that, learning embeddings by tracking patches of similar objects, they act as a very strong, supervision signal. And predicting visual representations, they also enable scalability. It also like helps train models that are generalizable as anticipation models for improving forecasting systems that can be used, has multiple use cases, specifically in autonomous driving scenarios. And this opens new avenues for integrating model based reasoning and intuitive physics in self supervised learning frameworks. And finally, we come to the last part of these, sequence of papers. It's videos for unsupervised image features. So the current self-supervised methods, they focus on invariant representations such as scale, color, and translations through these synthetic augmentations, right, which are popularly used like crop, flip, blur, and so on. And also these, what we have seen previously is that, these natural videos instead provide a very rich signal, which, that can be crucial for learning these intuitive physics and reasoning. So some of these signals are like perspective distortions, their pose and different kinds of motion and so on, and this acts as a very strong signal as compared to these handcrafted augmentations. So one way to kind of, improve representation learning using these natural transformations is to kind of, just distill them into image based representations. And this is something that, the works that we are about to like talk about or discuss basically do this. Is from Nikhil Parthasarathi and colleagues. It's called self-supervised video pre-training yields human aligned visual representations in Europe's 2023. And the high level idea here is that it enforces temporal equivariance of masked features across temporally displaced views. So given two frames from a clip, they first kind of obtain different augmentations corresponding to the object here. The way they kind of obtain these masked features or enforce the temporal equivariance of these masked features is by first predicting the attention map corresponding to the object, and masking the features using this attention map, and enforce, similarity in the feature space of these masked features. And when they pre-train their model with this objective, it results in really good performance in many downstream tasks. The next line of work is from Shashank and colleagues. It's called self-supervised representation learning from flow equivariance in ICCV 2021. So the idea, high-level idea here is they kind of enforce the flow equivariance, as the title suggests, and this means that they apply a flow transformation to the features of the current frame to predict the features of the next frame. And one of the limitations of this work is that solely relying on equivariance objective and lack of invariance objectives may also sacrifice some high-level representations, since when using heavier readout headers. From Deepak Pathak and colleagues, called Learning Features by Watching Objects Move in CPPR 2017. And the high level idea here is that they use motion information to segment moving objects and enforce the convolution network to predict these segmentation masks. So here we can see on the right that given a video clip, they kind of use an unsupervised non-local consensus algorithm to kind of obtain these initial segmentation masks, which is of the objects that is in motion, and then and use this as pseudo labels to train the model with the segmentation masks generated by the convolution network of the moving objects. And in this way, they kind of train their model end to end and show really good performance on many downstream tasks. However, one limitation of this approach is that sometimes they fail to segment the objects in noisy data, such as in cluttered scenes and so on. And another limitation of this approach is that it often fails on videos in the wild. And this is because of the assumption that there is just a single moving object in the video is basically not satisfied in long videos, which is made up of multiple shots showing different objects. Um, and so I have noted down all the different works in that basically train image encoders in a self-supervised setting from videos. However, if you find any missing works of yours or any works that you're aware of, feel free to please send me an email, and I'll kind of update this list of papers. And this is the most comprehensive list that I found back from 2002 to until like 2018 and so on. So finally, just want to say that the field of self-supervised learning of like image encoders from video has a very rich history, and now it's time to get back to it. So thank you so much.